Okay, here we go. All right, now we're cooking. That's not what I meant to do. There we go. All right, so we took a look here and we saw that the solute is less than the water. So therefore, this must be hypo because we have more water. And when we look at the outside, we see that we still have more water than solute. So this must also be hypo. All right, but now moving to part 2 that everybody really wanted to get into here. Part 2, let me get my arrows in a different color here. So for part 2, it says to draw arrows in each of the diagrams to show the direction or directions osmosis would occur in, okay? Osmosis is the movement of the water across a semi-permeable membrane, okay? So in this case, right, we have more water on the inside than on the outside. So which way would the water molecules move? Would they go from inside the cell to outside, or would they go from outside to inside? Which one would it do? Drop that in the chat for me. Which way do you think? Inside to outside? We're talking about for A. We're looking at A for right now. Which one would it be? Going from inside the cell to outside, or should it go from outside to inside? We got more water on the inside, so. All right, we see some people saying that it should go this way. Okay, any other options? We do have more water on the inside than on the outside. All right, so we have somebody saying it should go this way. All right, any other options? Anybody saying that it should go both ways? Because that's an option too. No? All right, no takers? All right, so the water always goes into the area that has the less amount. So it should go from high concentration to lower concentration. So it should be. Okay. Should always go from high concentration to low concentration. So what's going to happen to the cell? Is the cell going to be bigger or smaller? If it loses its water, what's going to happen? Think back to that gummy bear. It's going to get smaller, right? Because most of the cell here is made up of water. So if the water comes out of it, then it's going to shrink. This one is going to be smaller. Okay, all right, I can't write. Don't make fun of me. This one here should be smaller. All right. Okay, cool. Let's look at the next one. Yeah, I know you guys know the answer, just see. I know, okay. But let's do it one at a time. B here on the other side, on the other side. What's gonna happen? Out here has a lot less water. A lot less. This one is gonna be smaller, but it's not gonna be that much because it's only 5% difference. That's barely gonna do anything. Okay, but look out here on this one. What's gonna happen in this one? Which way is the water gonna go anyway? Is it gonna go from out here to inside, or is it gonna go from inside to outside? That's gonna happen. Inside to outside, right? And this thing is gonna be extra small. It's gonna lose a lot of water. 85 to 25%, that's gonna be a lot of water loss. Okay, so this one is gonna be very small. Very small is what we would predict would happen to that cell. Okay. All right. What about this one here though? Now here comes the trick that you guys already saw from before. Is it going to go from inside to outside or outside to inside? What's going to happen? Janai, I know that you had this one before. All right, I see what you're saying there, Lisette, but think about this. It says here, draw arrows in each of the diagrams to show the direction or directions osmosis would occur in. So there you go. That's the one. Should be both directions. So I'm gonna do a double-sided. Okay. I'm gonna do a double-sided. That's because it's going to, some is going to come in and go out, but it's going to pretty much be the same. So what's going to happen to the size of this thing? Is it going to be smaller or larger? What's going to happen here? What do you think is going to happen? It will stay the same. Okay. These are going to be the same size. Not much change at all. Okay. Not much change at all. I missed the P there, didn't I? Okay. Anyhow, that's what it should be. Take a minute here to update your work. Of course, yours don't have to be as jumbled as mine. You can put all that stuff over here. I just do it this way so that you can see. All right, I'll pause and take a look at your work, give you some feedback. All right. All right, perfect. All right, great. So now we're going to move on to slide number 2. Okay, great. Now, here on slide number 2, move these things out of the way for you. I want you to write your initial thoughts in the text box below of how do cells get what they need. Okay, we do know that they need nutrients, they need oxygen and all these things, but how do they get it? Keep in mind what we just talked about, how things move across a semi-permeable membrane. All right, keep that in mind. Today, we're going to create and or use models to explain the structure and function of cell membrane components. We're going to then explain how materials move into or out of the cell across the cell membrane. Okay, so we're going to be really focusing on the cell membrane today. In my other class, we did not get past everybody writes. So I'm thinking that we're just going to be doing our building a body of evidence, and that should take us through the end of class. Next time when you come back, I'm going to ask you guys to get started on your biweekly. Of course, you can do this when you get home. You can do the rest of it for homework, but pretty much for homework today is going to be deepening the understanding all the way through your exit ticket and feedback. But the bi-weekly we can do when we come next class. All right. So with that said, let's take a look at what you guys said here. See if you guys are onto it. Transporter nutrients. I like that. All right, through the cell membrane. Okay. Osmosis. Yes, there we go. Cutthroat Vikings. I like that even better. Not necessarily what we're talking about, but I like the Cutthroat Vikings for sure. All right, digestion, okay. All right, so let's take a look at how this actually works. Okay, so I'm going to give you an overview so you'll have an understanding of how to answer these questions. Now here is our big diagram that we're going to take a look at. We're going to spend some time on this one. Now, the first thing that you'll need to do is count up how much is on the inside and how much is on the outside. The reason for that is so that you will notice something happen. You'll notice that on the out, let's take a look at gases, for example. The gases, you'll notice that on the outside, you'll have a high amount, and on the inside, you'll have a low amount. Now you'll notice that the arrow goes from high amount to low amount. Okay, is that coincidental? No. If you look over here on these red ones, you'll count them up and you'll notice that outside is a high amount, and on the inside, there is a low amount. And then the arrow goes from high to low. Okay, what about the other way? Other way, you'll notice here with these proteins over here, that on the inside, there's a high amount, and on the outside, there's a low amount, and it goes from a high amount to a low amount. Okay, so question 2 here is asking you to describe the direction of the movement of the molecules in the diagram. Which way do they go? Based upon what I just showed you. Okay, that's for question 2. Question 3 here, how is the movement of gases different from the movement of the other molecules? So you'll notice that pretty much all the other molecules, they can only come into the cell through these protein channels here, protein channels. However, the gas, on the other hand, there is no channel for it to go, but it somehow gets in there. How does the gas get in there? Right? And the final question is based upon what you see here. There's different rates. Based on this idea, what inferences can be drawn regarding the rate of the movement of the molecules, right? So that's the big overview of the questions that you're going to do. I'm going to give you 5 minutes here, or 10 minutes here, to go ahead and answer those questions. And while you work, I'll give you some feedback so that you can use the feedback to make your answers better. All right, I'll leave this up here so that you can see this big diagram. Then I'll come and check in on your work. All right, so most people are almost done with their table for question 1 and annotating their graph. Okay. Great. You just need to count up those thoughts there. All right, for question 2 here, you guys are close, but I haven't seen anybody get it yet. So let me review a little bit here. What is the direction that the molecules move? You can't just say that they're moving inside, because there's some that is moving inside and some that is moving outside. There is a trend amongst all of them. There is a specific way that they go. The specific way that they go is based upon how many or what concentration it is. It always moves in the same way for the concentration. It moves from a high concentration to a low concentration, whether that means from outside to inside or from inside to outside. It's always the same direction, high concentration to a low concentration, always the same. Please add that to your number 2 response. High concentration to low concentration. That's always the direction that it moves, always. All right, great responses for question 3. Those are all good answers. No problems there. Let's see if we can crank out answer to question 4 in the last 2 minutes here. Then we'll be all set. All right, 30 more seconds. Listen, I think you have an excellent response here, way above what is really required, but we'll use yours as the model. Let's take 1 more minute here to finish up your responses. This is question 4, team. Great job, Lisette. Alrighty. So moving on to slide number 4. All right, here in slide number 4, we have a new diagram. And this one is going to deal with quite a bit of variables. So the first thing I want to do is identify what does the word polarity mean. I'm going to put that up here. Of course, I like black, so I'm going to put mine up here. Okay, polarity. A molecule that has a charge. Okay, so a charge is either plus or minus, positive or negative charge. Okay, that's what polarity is. So you can imagine that something that is non-polar would mean that it doesn't have a charge. Okay, don't think we have to state that. I think we already know. Something that is polar has a charge, non-polar, no charge. Okay, got it. Now, here we go. In our diagram here, we're still looking at the cell membrane. Our whole lesson today is about the cell membrane. And when we look closely at it, we'll see that a part of the cell membrane has a charge. Okay? So if you look up here, you'll see that the head of the cell membrane, this red circle here, has a charge. But these yellow tails here does not have a charge. They are non-polar. Okay, so keep that in mind. Now, other pieces of information to know is that the head part is hydrophilic. Okay, you'll find out later on that hydrophilic means that I need to draw myself a nice heart here. Love water. Okay. And then hydrophobic, like if you have a phobia of water, some people who don't like to take showers are hydrophobic. Hopefully none of you are that way. They no, that's not it. I don't like water. Okay. Hydrophilic, like water. Hydrophobic, don't like water. Okay. So far, we know polarity means that it has a positive or a negative charge. Non-polar means that they don't have a charge. Polar means that they have a charge. Okay. We also found out that this phospholipid bilayer or the cell membrane has a head that is polar and a tail that is non-polar. The head is also hydrophilic and the tail is hydrophobic, which is to say that the head likes water and the tails do not like water. Okay, so where's the water in all of this? Outside of the cell is watery and inside of the cell is watery. If you remember from slide 1 today in our do now, our cell outside, inside the cell has some water and outside of the cell has some water. Okay, so it's the same idea over here. Okay, outside has water and inside has water. Hence the reason why this might be shaped the way that it is. All right. Now that we see that, we notice here that gases don't need a protein channel for it to move through. It just goes right through, man. Gases walk through walls. But proteins, on the other hand, they need to go through these protein channels. We have these little blue molecules here that can't go through. And we have these little red molecules that can't go through this barrier. Only things that are coming in are these proteins and gases. That's all that comes in and go out, right? These blue ones and these red ones, they can't come in and they can't go out. All right. we now know that these blue ones here are nonpolar, but these proteins here are polar. All right. Now we have all this information here. Should be able now to answer these questions down below. Let me put this big enough so you can see all of this stuff. Should probably move this down closer. There it is. So that we can see everything. I'll pause the screen right there. And then I will take a look at you guys answering the question. We're going to take another 10 minutes here to answer these questions. Let's see what you guys have. All right. All right, let me give you another minute here to finish annotating, and then we can jump into question one, because it looks like people are stumped on question one already. So let's take another 30 seconds to finish annotating. Then let's take a look at question one. All right. So let's take a look at question one here. Question one is asking, what two major types of biological molecules compose the majority of the cell membrane? Okay. So let's take a look at the cell membrane. What do you see there? What is the most abundant thing? Well, you have this phospholipid bilayer, and then you have these protein channels. What is the phospholipid bilayer made out of? Well, since we haven't discussed this before, I'm just going to highlight it right there for you. Okay. The phospholipid bilayer is made out of lipids. What is a lipid anyway? Anybody knows? Drop that in the chat. What is a lipid? What's that? What's a lipid? Lipid. What's that? There you go. According to Google, I like sentences that start that way. Lipids are just fats. Okay, so lipids are fats. Same thing. Don't let anybody tell you that fat isn't important. We all need fat. Problem is having too much. Too much of anything is not good. But we do need fat. That's what covers our cells. They're made out of fat. That's what gives us this nice lipid bilayer. Okay. All right. Yes, yes, Amira. There it is. The second would be proteins. Okay. These protein channels are made out of proteins. Okay. So we got fat and protein. Sounds like a healthy diet, right? So we got our fats and our proteins. That's what the two major things are. Oh, up here? This is the key. This is just to tell you what these things are in terms of their polarity. It doesn't really tell you what the blue thing is, what the black thing is. It doesn't tell you what it is. It tells you what their polarity is. Okay. So you needed to look at the bilayer right here. says what two major types of biological molecules compose the majority of the cell membrane. This is the cell membrane, so you should be looking here. Okay, so that's just made up of fats and proteins, pretty much. Okay. Now the second part says, in what form are they found? Okay, you tell me. What are the lipids in here? What form is that? What does it look like? Okay, you tell me, what does that look like? You tell me what the proteins look like. Yes, there it is. So the lipids are in a phospholipid bilayer. Bilayer means two layers. So if you notice, you have one layer on top right there, and then another layer down below. It's a bilayer, it's two layers. Okay, what about the protein? What form is the protein there? Hey, trilayer? No. What are these blue things right here? What are those? What are those? The protein channels, okay? Right here, protein channel. Okay, so we got the, we have the phospholipid bilayer, we have the protein channels. What about this right here? What's that? You also got some surface protein. There you go. Okay. So all of that makes up the cell membrane. Okay. Of course, I don't expect you to have this. I expect you to have a sentence. So ensure that you have sentences. All right. So now that you are unstumped for question one, you know what hydrophilic and hydrophobic and all those things mean, and polarity and whatever else. I'm sure you guys can take the next 10 minutes here to do questions 2 through 6. All right, I'll leave this up here so that you won't be stumped. I'll put 10 minutes on the clock so that you guys can finish that one. Excellent job, Janai. That's what I was looking for. All right, team, your number 2 answers seem to be going well. We have 3 more minutes. See if you can put a little bit more pep in your step so we can finish out these questions before it's time to go. All right, for question 3, see that we're struggling a little bit. For question 3 here, let me give you guys some help. All right, here in question 3, I'm gonna remove everything. Here in question 3, it's asking about why is it that, let me read it. Water is a polar substance. Why is the phospholipid head hydrophilic and the phospholipid tail hydrophobic? Now, if you remember, you said that the head over here is polar, okay? While the tail is non-polar, okay? Tail is non-polar. If water here has a charge, sorry, it's wrong color. If water here is polar, right? Just like the head, and the head is hydrophilic, what does that tell you about polar things? Now note well, the tail is non-polar, and the tail is also hydrophobic. What does that tell you about polar things and non-polar things? Do they repel each other, or do they attract each other? Which one is it? Do they repel or do they attract each other? For question 3. All right, so I'm hearing a bunch of answers. So let me ask it again, just to make it clear. Does polar, like the water and the head, do they repel each other? Polar molecules, do they repel each other, or do they attract each other? Just the polar. Now we're cooking. Polar molecules attract each other. What about polar and non-polar, or the water with the non-polar tail? Do they attract each other, or do they repel each other? Do they repel? Oh, okay. Sorry, this thing is in the way. The water, which is polar, and the non-polar tail. Does the polar attract or repel non-polar? They repel each other, okay? Therefore, because these two are are opposites, this one is non-polar and this one is polar, therefore it must be hydrophobic. Doesn't want anything to do with something that is not like it. Okay? Whereas the hydrophilic head loves the water because they are both polar. Okay? Use that to help you answer question 3. See what you have. This is question 3. Oh, all right, hold on. 1 second there, listen. You guys gotta go. No. All right. I'll repeat this, then that's it for class. Okay. All right, let me put that up there. Have a great day. You guys gotta go. All right. I'll just put this up on the Google Classroom right after so that you guys can take a look at this later on and use it to help you finish your homework for tonight. Everything is due up to lesson 9, or up to slide 9. We'll do the bi-weekly when we come to class next week. Everything else due for homework. I'll put up this recording online. All righty. Have a great day, Fernando. Thank you very much. I look forward to it.